Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. You are invited to join us for the very first TWIMLcon conference, which will focus on the tools, technologies, and practices necessary to scale the delivery of machine learning and AI in the enterprise. The event will be held October 1st and 2nd in San Francisco, and early bird registration is open today at TWIMLcon.com. Again, that's TWIMLcon.com. I can't wait to see you there. All right, everyone, I am on the line with Laurence Watson. Laurence is a data scientist at Carbon Tracker. Laurence, welcome to This Week in Machine Learning and AI.
Hi, Sam. Great to be on the show.
It is great to have you on the show. Let's get started by exploring a bit of your background. You started out in physics, made your way over to climate change policy, and now you're working in data science in that field. Tell us a little bit more about that path for you.
Sure. So when I was small, I always wanted to be a physicist. I just love to ask why and to get down to the root of the question. And when you got to the fundamental of the laws of the universe, I thought that was far enough. But when I finished my degree, I really wanted to have a positive impact or to address some of the issues that needed addressing in the world. So I decided to try and work on clean energy and energy policy. I worked with a think tank that campaigned to reform the European carbon markets. And that was when I got started into programming. They had a Python and Django stack, in fact, and I sort of took over looking after their database, scraping the European Commission's website where they released all of the data about who was buying and selling these emissions permits. And then went from there, really. And I've been at Carbon Tracker almost 2 years, trying to convince the financial markets about climate risk.
When you say trying to convince the financial markets about climate risk, what does that entail?
Sure. So we, Carbon Tracker, popularized this idea of a carbon bubble, that if the valuations of fossil fuel companies are to some extent based on the amount of fossil fuels they're going to sell in the future, if they're wrong in their predictions and those valuations are in fact going to be constrained by climate change, either by economic factors or by governments saying, you're not going to be allowed to continue in this way, that has a financial implication. So it's all been about quantifying the extent to which they're going to face those risks.
Practically, what does that mean? What is the Carbon Tracker, product or service that works on this quantification?
So we've done a lot of work on oil and gas, and then I've been working on coal power. For oil and gas, we put all the oil projects on a cost curve. So we say how much does it cost for company X in this region to produce a barrel of oil, and then we say how much oil could we burn in a climate compatible scenario, and the projects that are above the line don't make it in. And so we say, some companies are better positioned for this energy transition in a climate compatible way and some aren't. And then we started doing the same for coal power, saying if there's going to be a coal power phase out in a given country, how should that be done? If it's done on a least cost basis, which company has the highest cost units and should therefore be closed down first? And that is about the market as well, because I'm saying close down, but it may be that the market sends a signal such that the coal plant is no longer economically viable, and that phase out would happen in the same way.
And so who are the users of this intelligence? Is it the policymaker or the companies themselves?
We think we have some appeal to a lot of different audiences, definitely policymakers, because they need to be aware of these forces that are going on in the energy transition and make sure the policies are there to support it. But in investors, certainly, because we think there's a lot of shareholder value at risk for companies that aren't prepared for the changes that are happening. We've seen that a lot in Europe in the utilities sector, where European utilities lost a lot of money because they didn't see renewables coming. Essentially, but also to campaigners and journalists as well.
And so where does data science fit into all of this?
So we take a lot of different databases from all sorts of different sources and try and join them up. But the project that we've done more recently was really about looking at places where the databases weren't so good, where it was very hard to get publicly available data about the kinds of operations that we're trying to find out about. So trying to find coal production data, trying to find out about how plants in India have running their pollution technologies, all of which has impacts on how much they cost to run and the profitability of the companies. So it's about joining up different data sources, making them talk to each other, and about filling in the gaps where we don't have good data.
So walk us through the process. How did you go about pulling together all of these data sources?
So firstly, I have to give thanks to all of the data providers all around the world doing a huge amount of good work in terms of making it. I mean, we buy a lot of data sets, but there are also some really good freely available public data sets, including Coal Swarm, which have a global database about operating coal plants, which I know is a lot of work and really a testament as well to open source, because they have a website a wiki site where people can upload information. So they aggregate that and do a lot of work themselves to put it all together. Of course, there's no uniform naming as is often the case. So we have to do a lot of sort of string matching and pattern matching in order to sync up where we think these projects are and bring together these different qualities that we're looking for, basically, in terms of capacity, in terms of ownership. And these things are often some organization may be really interested in what is there, but a different organization may be really interested in who owns it and how that ownership structure has changed over time. So gluing those things together. And in terms of how we do it, because Carbon Tracker has a lot of ex-City analysts, so we do a lot of analysis in Excel. And so my sort of first task in the beginning was to interface with a lot of existing Excel databases and put them into SQL, which is usually what I would use. And then just a lot of string matching. They're not terribly exciting at the base layer, but essential for everything we did on top.
Okay, and then you're doing some work with satellite imagery as well, is that right?
Yeah. So why don't I just jump in and tell you a little bit about that project?
Okay.
And so what we wanted to find out was the capacity factor of coal plants. And the capacity factor is simply how much of the time, what proportion of the time they're running compared to their theoretical maximum output. And that's a key part of the financial evaluation of any plant, because the profits that they can make are a balance between the revenues they can earn when they run and the ongoing costs and the fixed costs that they have to pay every year in terms of maintenance costs, in terms of lifetime extensions, and other fixed costs. So working out how often these things are running is a really important part of our modelling. Now, for various parts of the world, that data is public, though sometimes it's a few years out of date. So in the US and in Europe, you can find that data through the EPA, and in Europe through it's called ENSOE, which is about electricity transparency. But the data's out there. But for other parts of the world, particularly sort of Southeast Asia and across Asia, that data was not available. Or if it is available, it's about 4 years out of date. So we wanted to investigate whether we could use remote monitoring, that is satellite imagery, to answer that question and work out how often these plants are running. And we thought we had a good shot at it because at the same time, the proliferation of competitors in the satellite imagery space and the availability of the data has just increased hugely in the last few years. Partly that's to do with these nanosats and CubeSats, which are very small, but still give reasonable quality outputs. And some companies like Planet, who we worked with, has put up a sort of over 100 of these, I think 150 now of these CubeSats. And I know a lot of other providers are doing the same, or certainly thinking of if they're not already.
The goal then is to look at areas where you've got known coal production facilities and try to predict their output, their capacity, at any given point in time. And it sounds like one of the things you're doing is you've got some known facilities and their output via the ENSO-E and EPA, and you're using these as labels to then train a model.
Exactly. That was our starting point, that we would have all this labeled data, and thus we would have a strong base to do some proper supervised learning. And so we without too much further scoping, we then set off to try and do that. And possibly, as with all things, perhaps we should have spent longer scoping out or thinking about other kinds of solutions. But hey, we just dove straight in, and and I started writing scripts to interface with these satellite providers' APIs, where you can query for images and things. So the first step was to create GeoJSON objects specifying the areas. It's called areas of interest, or AOIs, what's referred to by these satellite image providers. So we had to make shapefiles or GeoJSON files for each one of these coal ponds that we wanted to get the data of. And I just drew a square, a sort of 1.5 kilometer squared size shapefile around each plant. And sent that off to the image provider's API and said, give me all the images you have in the last 2 years that meets a threshold of cloud cover of, say, less than 10% cloud cover, and let me download it. And that was amazing in the first instance, because that sort of capability, again, is very new, because usually, or what has historically been the case, was if you want to work with satellite data, you get image tiles, and the tiles are like the photograph, the image that the satellite sensor takes, and it covers a large area, and it's a big file. So if I wanted to do that historically, I would have had to download sort of terabytes of data and then sort of clip it myself. Thankfully, I didn't have to do that. I could create a labeled set of small images, where images were a few hundred kilobytes each or something, because they had been clipped out. I think Digital Globe call these image chips. So reasonably quickly, we had a data set of around sort of 80,000 images for the US and the EU labeled. So we were sort of ready to go relatively quickly, though there were some challenges in there in terms of making sure that the time zones were right for the labels and the satellite images, and syncing that up correctly. That was a minor headache. Another challenge that we saw straight away was that we didn't have any sort of balance in terms of the training classes. If we were going to look at whether plants were running very hard, or they were running somewhat, or they were off, or if we were just, as we ended up just looking at whether plants were on or off, it was very imbalanced classes. And part of that is because satellites take images in the daytime, plants also happen to run more in the daytime. So there's no images at night when plants are running less and more likely to be off. So we had very imbalanced training classes straight away that we had to deal with them, which we counted just by sampling the imbalanced class multiple times, and then doing lots of manipulations to it, and that worked out. It worked out okay, but not fantastic, I would say. And so that was one limitation that we saw straight away.
And were you primarily looking at this binary status, whether the plant was on or off, as opposed to trying to measure the plume area and try to determine the output in some way?
Initially, we absolutely wanted to be hoped. We had high hopes that our model would just spit out a reasonable output number for each plant, and that had to be calibrated on the actual capacity, the size of each plant, which we had. We had that information, but unfortunately, so we tried to just make a regressor. But it didn't turn out terribly well. The results it gave didn't seem to reflect reality particularly, and part of that we we found by doing some manual analysis was just looking at the classification that it was doing in terms of the actual pixels that it was counting up, and this is where perhaps an early weakness that was I think I made a decision early on to take visual images from the API, which is author rectified sort of RGB images, because visual images are what's needed, of course, to do an image processing machine learning technique. What's also available is 13-band analytic images, which contain a lot more information. And we ended up using that to do the counting up rather than doing a visual classifier, because any kind of very light pixels, which could have been to do with reflectivity of metal, other kinds of sort of smoke plumes and things coming off the ground, that was all getting counted up and sort of adding to the plant's output, which wasn't a good reflection of what was actually going on. So fairly quickly we decided that we weren't going to be able to get the output using this method, and so we ended up doing on Google Earth Engine we made an algorithm that would count up the pixels in each image and just say, using the analytical images, because it could do a spectral linear mixing of the information in those analytic image chips, and that gave us a better estimate of an instantaneous output. So our idea then was to combine these two different techniques to say, here's when we think the plant's on or off, and here's what we think is an average of the plant's output over that given time. And by combining them, we got to a reasonable result in the end.
You mentioned earlier that a lot of your challenges could be traced back to kind of the way you scope the problem or problem definition. And this is one example of where you needed to pivot in the way you approach the problem. Are there others that we can talk through?
Yeah, certainly. I mean, one thing that became clear to us over time as we got more into the problem was we started out really wanting to understand China and what's happening in China. And of course, from a climate change perspective, China is a huge global emitter, and it has a huge amount of coal capacity. It has sort of 1,100 gigawatts of coal capacity. So from a climate perspective, it's very important to know what's going on. And historically, the data has been very poor, and China's been criticized for publishing statistics that perhaps don't really reflect what's going on, and that sort of thing, or the data is only available years later. And what we found as we started working more and more closely on this and talking to more and more people who were closer to the ground, was that more in recent times, in fact, there is a real-time monitoring effort in 5 Chinese provinces. So we were actually able to obtain very good, high quality granular data for coal emissions in some of these places, which was brilliant because we could then calibrate the predictions we'd made for China in those regions. But then, of course, it to some extent reduced the need for the methodology we'd developed. So we were sort of happy, pleased, and frustrated at the same time with that. But then, of course, that was only for 5 regions. It was only it's only mandatory in certain places. So for other places, of course, we can still use our methodology and be even more certain or confident in the results that it gave us.
Did you find that the models that you created translated well from one region of the world to another, or did they not?
Yeah, we did, and I think the interesting variation, in fact, was to do with the ground state of the plants. Oh, and yeah, here's another good challenge that I'd forgotten about, or maybe my mind had tried to push it down into my subconscious because it was so annoying. So just to make it very clear about how we were trying to do this, we were looking at the visual plumes, the smoke, the water vapor that come out of the flue stack and the cooling towers from a coal plant, and we were testing and sort of subsetting on various sort of samples to try and improve our results. And I forget how exactly we stumbled upon it, but as soon as we did, it became so obvious that there are various kinds of cooling technologies that coal plants have. There's what's called once through, which is if the plant is located near a body of water, it'll suck in water from, say, a lake or a river, use that to cool its equipment, and then pass it out a slightly warm stream of water. And there's also active and passive cooling towers, which is draft cooling towers, where evaporation is used and produces these huge steam clouds. Now, those two cooling types, produce very different cooling plumes, and the once-through method, in fact, did not behave very well in our models at all. So once we were able to slice that out and only examine plants with active and natural draft cooling, we saw much better results. So that was a real a sort of step change that perhaps if we had a deeper understanding of the physical characteristics of coal plants at the beginning, we could have seen coming. As it happened, we were able to infer it by looking at the results as we went along.
It also strikes me that, for example, wind would make a big difference. If there's no wind, you're going to have this plume that kind of goes straight up and doesn't spread horizontally in your image. But if it's very windy, it'll kind of disperse in, one direction, and your model would need to be able to figure that out to perform well.
Absolutely. We did do a reasonable amount of investigation against environmental data. And what really enabled us to do this was Google Earth Engine, which had a lot of environmental data layers that we could just bring in very easily. It would have been much more difficult if we weren't using Google Earth Engine, I must say. Though other platforms offer similar things, but we were able to use that to get per image a wind speed, a wind direction, temperature, atmospheric pressure, and humidity. And so we did some analysis against all of those variables to see if there was significant correlation with plume size. And with wind, we did find if the wind isn't blowing, the plume goes straight up and doesn't disperse so much, which when you're looking over vertically. And some satellites, in fact, do offer an angle offset so that you can try and do volumetric estimations. That was something that we left on the side and didn't end up trying to investigate. That was sort of beyond the amount of time we had. But so if the wind is very low, you get the straight up plume. If the wind is going somewhat, you get more of a dispersal. And if it's very strong wind, then you get more of a straight line. So actually the plume area looking from above isn't as great as sort of medium wind. But overall, we didn't find that it was hugely significant. Same with the other estimates, because we hoped that by bringing those variables into the model, we would able to get a really good accuracy, but they didn't actually help as much as we had hoped, unfortunately. And I think that was when I talked about the scoping. I mean, we didn't know how hard this problem was. I think is the real truth of the matter. And and when you just look at the noise and the variation of generation output compared to the plumes emitted by a plant, you just find that there's a huge variation. It's just very noisy to start with, and so the accuracy of what we could end up with was always going to be limited by that natural variation. Whereas if, for example, we were just trying to quantify what kind of equipment or what kind of cooling technologies, or say we were doing something different and just looking at, whether solar panels are built in a certain area, static stuff that, rather than time series data, that's a lot more. I think you can get a much finer degree of accuracy than trying to get something dynamic like this.
Right.
But
right.
So we lived and learned.
And so the availability of these image chips helped quite a bit. But did that totally alleviate the data preparation challenges, or did you have other areas where data prep was really a big challenge for you?
Gluing everything together at the beginning was some challenge, but beyond that, I mean, that just the amount of cloud architecture and cloud solutions that are being offered really does a lot of the work for you. And for example, AWS now hosts a lot of archived satellite image data sets that anyone can access, which we investigated. We didn't end up using. A lot of these satellite image providers now have their own platforms, and they really try and take as much out of your hands as possible, so you can really get to the implementation phase as quickly as possible. And it's entirely possible to do extremely rapid prototyping now with new kinds of image classifiers on satellite data, whether that's through Google Earth Engine, which you can just pull in all sorts of different sources, or through one of these. Mostly, I must say, they're proprietary, but a lot of them have sort of quite low barriers, especially for academic institutions, and a lot of them have not-profit elements as well. Of course, they have huge fixed costs because they put satellites into the air, and they need to make a return on it. But they are very keen for people to try new things and to, well, they hope make commercializable solutions. And I know, for example, Planet had a Kaggle challenge a while ago about classifying bits of the Amazon rainforest to try and get people working on these different challenges. And I know that there's a huge amount being done across the sort of NGO and energy climate change space on all sorts of things around water, around coal mining, forest cover, afforestation, all those sorts of questions, which can, as I say, I mean, we are a Carbon Tracker. It's and people that work this project. It was only sort of maybe three of us, and the fact that we could even pull together a sort of a machine learning project with satellite images, I think, says a lot about how quickly you can get up and running with modern tooling.
For the classifier that was looking to predict the status of the plants, what model did you use? You said it was a visual classifier, so it's like a CNN.
Yeah, exactly. It was a CNN. We used Inception v3, and we just wanted an image processing model that knew edges and knew its way around an image. We ended up stripping off some of the last final layers, and I think we added a dense layer. But we didn't have to do a huge amount of tweaking. Maybe we should have done, but we didn't. That was what we ended up doing, and it worked pretty well, pretty okay, I would say.
You were evaluating your model performance based on, again, this kind of these known U.S. and Europe plants, or did you end up with something different?
No, we just used the label data for the US and the EU, and later when we found out about this source in China, we were able to do some training using the labeled China data as well. And so we just looked at precision and recall for the plants that were on and the plants that were off. And again, because of this very imbalanced data set, that most of the images were of plants with some sort of smoke vapor plume. We had very good accuracy or very good precision for plants that were on, and then much worse, in fact, for plants that were off, which dragged the accuracy down overall, which is but understandable with a very balanced training set.
Out of curiosity, what's the typical kind of cycle time for these plants being on or off? Are they cycling, several times a day, or is it, they're cycling for, days or weeks on end?
So there's a cost if you're a coal plant operator to go down to zero. It's if you have to start up against what's called a cold start, and it's much easier to just lower your output. So plants are sort of ramping their outputs up and down quite a lot. But then they might turn off for a period of days. But most of the time, it's more useful for them to try and keep running as much as possible and to keep some inertia going. And for the classifier's point of view, that isn't very helpful because it's just saying, oh, it's still on, it's still on. And that was why the results that we got were. Initially, we thought we could have a really fine-grained time series and be able to see, every day or every time we got an image, whether it's on or off, and draw a very nice time series chart. And what we ended up deciding was that we could get reasonable accuracy over a time period because we could take these averages. But we weren't able to get, to say in this week what's happening. That was just a limitation that we found. Though as plants, in some areas, I know in the UK where the economic conditions are much more competitive for coal and they're really struggling, they are trying to innovate, which does mean cycling more often because they'll be trying to make sure that they hit the spikes in power prices, and then just sort of lay low the rest of the time. So, I mean, in theory, running these models hopefully will be able to identify some of these changing operating characteristics, or I mean, certainly spotting plant downtimes and things would be something that we would love to do in terms of just setting this running and then automatically flagging when things are changing.
Mm-hmm. And did you define off with regard to some kind of threshold to account for this, cycling down very low, or was it hard off was the only off that you were considering?
It's a good question because we came up with two things there, whether the pixel count would give a value at all, i.e., but then there was sort of generic noise in the images. And when you said before about how did the algorithm fare in different regions of the world, of course, the image is a square around the power plant. So it is getting some of the landscape. Of course, the landscape is differing all around the world, and we didn't know to what extent the CNN would pick up various bits of this landscape and other parts of the coal plant and try and include those, and including, of course, there's some sited on rivers and on coastal regions and things. So we really wanted to try and delve into it to ensure that wasn't happening and it would be repeatable. And so even when it was off, there was a base level of reflectivity. So. So in short, yes, there was some sort of threshold.
And so that's the classifier. On the regressor side, did you use the same sources, NSOE and EPA, for your training data or for your labels, or did that come from someplace else?
No, we did. We started off with the regressor and we did try to use the exact same training data. But we found that it just wouldn't converge, which was very frustrating. So we switched that pretty quickly, and we just thought this isn't going to produce good results.
You didn't get anywhere with the regressor at all, or you switched to a different approach?
Yeah, we just switched out and said let's just do this with a pixel counting method, basically.
Got it.
Yeah,
so. So this wasn't a machine learning. There was no training data. It was just counting the pixels and exactly. Correlating that to an output based on understanding of the underlying principles.
Precisely. And so of course we love to use machine learning where we can, but in this case we just thought, okay, we just need to get some number outputs here, and the simplest way looks to be best. I mean, of course, a huge challenge in terms of doing the pixel counting is that a white pixel and a smoke plume from a plant looks indistinguishable from cloud cover, though there is some stuff about sort of height and sun reflectance and those sorts of things. But essentially, for various parts of the world, and in Southeast Asia certainly very difficult, you're never going to get optical images frequently enough that aren't obscured by clouds. The reason why you could set a limit like 10%, that doesn't mean that there's 10% clouds evenly distributed. It means in an image, a large image tile, there will be some clouds somewhere. And so you just hope that doesn't intersect with the area of interest you're trying to look at. And most of the time it didn't, but some of the time it did. So that was another source of error with cloud cover. And there are some sensors that are less affected by this. There's a whole lot of sensors, including from the European Space Agency's Copernicus platform, that look at ozone, sulfur dioxide, nitrogen dioxide, and there's also some radar, synthetic aperture radar that will pick up on metals, and that's very good for looking about where things are being built or if there's industrial operations happening. And I know there's some very exciting analytics companies that are using that approach to regularly check on industrial applications or economic activity automatically. So their algorithms will just run every day and say, here's what we think the economic activity in this sector is based on this radar data.
How long did you spend on this project?
All told, I think we got the data at around Christmas last year. That's when I was writing the scripts to get the first training set, and it took us. I mean, we did other projects in the interim, so it probably took us about half two of our time for about 9 months, something like that. Maybe a little more than that, actually.
Okay.
I shouldn't really undersell the amount of effort it does, but it does no one any favors to do that. And it was really to fill in the gaps in a global coal economics platform that we have just been developing. We're going to launch. We're launching just at the start of December, which is going to showcase the cost and the profitability for every coal plant worldwide, as well as contrast it when renewables are going to be cheaper, or it'll be cheaper to build new renewables than to even run existing coal plants. So that's the data we wanted to make available. And that was why we were doing this project, such that we could fill in the gaps of places that we really couldn't find any data at all. So this project did feed into that portal for China. But over the year, we also tried to develop a lot of local partners. And so it turned out that talking to people and getting local expertise in all parts of the world was also a very, very useful way as well. And is that machine learning? I don't know. The human machine at work.
Interesting. And so are these models, are they kind of in a ongoing production state, feeding into this portal, or have you, did you kind of do a survey and then collect the data, and then is the portal presenting more static data?
Yeah, our aim is to update it every 3 months. While I had the ambition that I would sort of productionize everything and just keep all the scripts running. We ultimately didn't have the need to do that. We're a not-for-profit, so we're not selling. We don't have customers in that sense. So it never seemed like it was really necessary to do that. However, because it is really interesting for a lot of different groups to have this information, and this is where in the not-profit sector. It's very hard to get these sort of partnerships set up where someone builds it and everyone else uses it. But I have some hopes that will happen. And there is a lot of very exciting information sharing and technical methodology sharing across these different sort of technologies around the energy transition. And it's only going to improve over time. So hopefully our work will be a part of that in some way.
It strikes me that this is, just one really interesting use case around how machine learning, AI, data science can be applied in the sphere of climate change policy. Are there others that jump out for you?
Yeah, well, absolutely. I mean, the Paris Climate Agreement and the international agreements, one big part of that is about countries' inventories and holding every signatory to those agreements to account in terms of what they say they're going to be doing. And that means, and that's a whole industry in terms of monitoring compliance, monitoring CO2 emissions, because what falls out straight away just on our coal work is, if you know how often the plants are running and you know some other characteristics, you can estimate how much CO2 is being emitted. And there's a lot of satellites now that are just for CO2 monitoring as well as other air pollutants. So using AI, you can and data science, you can run automated algorithms to just continuously measure these things. And again, a lot of this data is available. It's just a question of gluing it all together. So I do see a future where everyone or civil society is able to keep tabs on all large polluters and nation states to say, are you really are you staying true to the commitments you've made on climate? Is this large polluter staying true to its commitments to run its air pollution scrubbers, or is it in fact, just pumping out pollution into the atmosphere and thinking it can get away with it? So I see that really starting to change in real time. And the other part of it is making arguments about the speed of growth of the positive side of the speed of uptake of renewables, of solar deployment, and also smarter predictive capabilities in terms of power systems. So being able to more accurately predict solar and wind output, shifting demand, and smart grids, so smoothing out the peaks in energy demand. which reduces the system cost for everyone and further erodes the case for fossil fuels. And of course, I mainly look at the power sector, but there's power also has a water stress and water impacts, which is extremely important. That's something that can very easily be seen, and changes over time can very easily be seen from space or in automated ways. Deforestation can now be tracked again in sort of near real time. A huge amount of applications, and I think the more people that we in the non-profit sector can sort of mobilize to work on those, the more data scientists we can attract to come and work on those projects, the better able we'll be to address them.
Laurence, thank you so much for taking the time to chat with me. I really enjoyed it.
Great. Sam, thanks so much for having me on.
All right, everyone, that's our show for today. For more information about today's show, visit TWIMLai.com. Be sure to visit TWIMLcon.com for information or to register for TWIMLcon AI platforms. Thanks again to C3 for their sponsorship of today's episode. To check out what they're up to, visit c3.ai. As always, thanks so much for listening, and catch you next time.